In this video, we will be doing 2's complement, okay, to represent both positive and negative 8-bit integers. Okay, so first let us understand this term, 2's complement. Okay, it's just a fancy term, nothing complex. It's just a binary representation of a decimal number. Okay, and in this binary representation, you can represent both positive and negative integers. Okay, that's it. So what? Let's say you want to convert x number, let's say 10, in 2's complement. 2's complement. You have to convert this number, decimal number 10, into 2's complement. This is simple. You just convert it into binary form. Okay, so what is 10 in binary? 10 in binary simply we have discussed in the previous videos, 1010. So 10 in decimal is 1010 in binary, and we can also say that this is a 2's complement. So see, nothing complex, just fancy saying that because this is a positive integer. So for the 2's complement of this decimal number is simply the binary representation. Now things become a bit complex when we find the 2's complement of a negative number. Okay, when we have to find the 2's complement of a negative number, see, in the positive side you just convert, let's say decimal 5, you convert it into binary, and this becomes a 2's complement. But in negative but converting a 2's complement of a negative number is a bit tough. Let's say you have -5, you can't convert this directly to 101 and say that this is a 2's complement. This is a bit different. What you will do in this case to represent -5 in 2's complement, what you will do, you have to first write the binary representation. So -5, you have number, you write the binary representation of this 5, that is 101. Okay, then you flip the bits. So what happens? First of all, write this 101 in 8-bit form. So in 8-bit form, we have a register of 8 bits: 1, 2, 3, 4, 5, 6, 7, and 8. So write 101, and then rest fill the register with 0 bits. Now you flip the bits. So wherever we have 0, it becomes 1, and wherever we have 1, it becomes 0. So 0 becomes 1, 1, 0 becomes 1, 1, 1, 1, then 0, 1, 0. So this you do first of all. Okay, after flipping the bits, okay, you just add 1. So just add, we have done in the previous videos, we have done binary addition. So when you add 1, it becomes 0 plus 1 becomes 1, 1 plus nothing here is 1, 0, 1, 1, 1, 1, and just write the rest of the bits as it is, 1, 1, 1, 1, 1 here. Okay, so you get this number. Okay, so now this is the final answer. Okay, so -5. Now what the 2's complement of -5 is? This binary number. Okay, so this is the final answer. So simple. When you have positive plus 5, when you have positive plus 5, 101 is the 2's complement. When you have negative 5, you just write this number in 8-bit form. Okay, write in 8-bit form, and then invert the bits from 0 to 1 and 1 to 0, and add 1 to it. So then that will give you the answer of 2, that will give you the 2's complement of -5 or any other number. Let us take another example. Let's say we have +5. To convert in 8-bit 2's complement, you just convert it into a binary. So binary form of 10 is 1010. Simple, right? Now let's say we have -10. -10, to convert into its complement, you just write the binary form, invert the bits. So 0 here becomes 1, then 1 here becomes. So you are saying you are just converting these zeros to ones, inverting it, and here we have 1010, here we have 0101. So you are inverting the bits, and after inverting, you just add one to it. So here one we add. So let us say here we got the number 1111 0101. After inverting, we add one to it. When we add one to it, now we know using the binary addition in the previous videos that 1 plus 1 gives you 2, and 2 in binary is 10. So 0 of this 10 comes here, and this 1 becomes the carry. So 1 plus 0 becomes 1, and rest of the bits you can just write as it is. So this is the final answer: 1111 0110. This binary addition, you can check the previous videos we have done using the carry method, because yeah. So what is the final like important? What is the conclusion? Okay, the conclusion is that the leftmost bit. See, the leftmost bit is called the most significant bit, and the rightmost bit is called the least significant bit. Okay, so the leftmost bit indicates the sign. So what does it mean? That see you see in this case the leftmost bit or the most significant bit had the sign 0 in positive 10, but in negative 10 it had the sign 1. Even in this case, you see in positive plus 5 you have the most significant bit had the sign 0, and the negative 5 had the sign 1. So this means that in 2's complement, a positive number or positive numbers more significant bit will always be 1. So in 2's complement, positive numbers most significant bit will always be 0, and negative numbers most significant bit will be always 1. Remember it. So if you have, let's say, plus 15, you will always have the leftmost bit, most significant bit as 0. And if you have minus 15, the leftmost bit or the most significant bit will always be 1. So this is what it means. So what is the use of two's complement? It allows negative numbers to be added easily, subtracted, manipulated using the same hardware that handles positive numbers. See, we have a register in computer or that stores the memory of the CPU for fast transactions. We have discussed about registers in the previous videos. So we need to handle both positive and negative numbers, right? We can or like we can't depend always on positive numbers. So this tools complement help us to do conversions using the same bits. Okay, otherwise there will be, because there is no thing as symbol in bits, right? Minus 101 or 101. Okay, you will have to represent bits. You will have to represent negative number using bits only without a sign. So this two's complement comes to the rescue. Okay. Now the third important point is when you perform arithmetic operations with two's complement, you don't need to distinguish between positive and negative numbers because the rules for addition and subtraction are same. Okay. And the last point, two's complement simplifies how computer handles both positive and negative numbers in binary, making it convenient for performing mathematical operations and saving hardware complexity. So if we never had two's complement, it will become very difficult for computers to do arithmetic operations using negative numbers. Okay, so this is the crust of this topic. We will discuss more in the next video.